So, okay. Yeah, I noticed that you're struggling a little bit to find good questions, so I will start asking some questions that occur to me when I'm lecturing. Okay. So, the key theorem that we're discussing and almost finished, I'm just spending too much time on this, I apologize, but I still think it's important, is the normal form theorem. And the statement, as you know, but I'll recall it, is we just think of it as the germ of a holomorphic function. Abusive notation. This is really the space of equivalence classes, but this germ of a holomorphic function. Then, after, well, let's say and f of 0 equals 0, just convenience. Then, after bihomomorphic change of variables, say W is a function of Z, f of W equals W to a well-defined invariant, the order of vanishing of f at 0. That's it. That's it. It's amazing how simple this theorem is. And the proof that we talked about, proof 1, was with formal, using formal power series. And being careful with conversions. And the second proof, which is more in line with my way of thinking originally, you obtain roots via the exponential map, fundamental construction in mathematics anyway, and use the holomorphic inverse mapping theorem. Both of these tools are very important in my mind. Now, the roots part looks like this. You define A, where A is some number in not 0, and you map it to A to the Z, if you like, A to the power Z as equal to X Z ln of A. You can write that down for me. Well, you know about that in over the reals. You're very familiar with that over the reals. But over the complex numbers, you have to do something. And here you need you need various things. You need the exponential map. Is a holomorphic map from C to C star, which is a homomorphism. Holomorphic homomorphism, globally defined, and it's locally biholomorphic. The reason is the derivative of this thing is the thing, and it's never zero. So it's locally biholomorphic, but one of the key things is that you're really going to need is, you need very badly here, that A is in the image of X, because you need this because you're going to take log of it, and log is the local inverse mapping. Log is the local inverse mapping. Log, or ln, is a local, not unique, inverse mapping. The picture you should keep in your mind, in my own opinion, is here's A, and we will see, in fact, that this is C, and this is exponential map, and here is there. We will see that there are various. There's no global inverse, but there's a local inverse. There's a local inverse biholomorphic from each pre-image of A. So on. If you like, maybe you say this is log sub 1, and this is log sub 2, and so on. We will talk about that in some detail right now. So we will see that, in fact, there's no global inverse. It can't possibly be, because these two things are not globally the same. They're only locally the same. It can't possibly. That's not a proof, but that's somehow the reason. So we don't need a global inverse. We take any one of the inverses here, but we have an inverse. In other words, that A is in the image, because you want to go backwards. So if you're unlucky and the image is like if it stopped here somehow, and A is over here, you wouldn't go in the image. You wouldn't. It's clear. You need A to be in the image. So you need surjectivity badly. So the proposition is if G is an open subgroup S of C star, then G equals C star. Another way of saying that, I looked at your homework this morning. I hadn't really proved that yet in the course. I proved it in the notes. But this is the fundamental thing. There are no interesting open subgroups of C star. Okay? And the key you will see is that C star is connected. Because in the proof of this thing you show that it's open and closed. And if it's open and closed, then it's everything. So I'll start writing little questions assume question. Assume that C is connected. Let's even say arcwise connected in a stronger sense. For me, it's stronger. So, arcwise connected. All these definitions are the same for something like C, complex plane. Y is C star connected. And then when you see that question, if X is connected, do we know that X minus a point is connected? Well, it maybe depends on what is X and what is the topology on X and so on. So I'll make this precise. Let's call this 1, let's call this 2. Question 3, how to make question 2 precise? Because it depends on what it means X connected, and therefore it depends on what it means X as a topological space. If X is some horrible thing, I don't know if this statement is true. I always worry about horrible things. But in my life, things aren't so horrible, so it's okay. Problem. So in other words, what maybe we need maybe a condition on that. And then question 4. See how easy it is, a professional mathematician, to start with something Mickey Mouse and end up with something maybe where I don't know the answer. Okay? That's what we do in mathematics. We start at question -5 and end up with question 1, which might even be a research project. Okay? Let X be a connected topological space. And then start asking yourself, what the devil conditions do we need? Maybe I always need Hausdorff somehow or another. Maybe you need Hausdorff or something like this. Maybe you haven't looked closely enough at these topological conditions. What is Hausdorff? Have you heard of Hausdorff? Yeah. Good. So it's a minimal condition that means you can separate points by open sets. It's sort of a minimal condition that anybody believes, but a lot of the times it's not true. So that actually a connected topological space, maybe arcwise connected, maybe a manifold. Maybe something really, maybe even a manifold. So a differentiable manifold or a topological manifold, something maybe even a manifold. So then I'm not afraid of anything, because manifolds have all nice conditions, and connected topological space, maybe even a manifold, and E, a closed subset. All of these questions here, this closed subset is the one point. But if you understand it for one point, maybe it's good to understand it for a closed subset. Under what conditions is x minus e connected? Then you start thinking, how bad, in other words, how bad is a closed subset? Right? Well, okay, 2 points, but nah, closed subset. Certainly you want closed because the complement should be open in a nice topological space. So that's an interesting, maybe even hard question. Rough answer that anybody, I write this on my scrap paper, rough answer, E should be small. Right? Somehow if you remove a small set, well, like a point, or 2 points or something like this, it's okay, but then you start thinking of a measure theoretic, something that's small is a circle. E is equal to a circle in R2, and that's not small enough because it divides the plane into 2 parts. Right? And then you heard from some professor going blah blah, what is the Jordan curve theorem? Have you heard of that theorem? You have a closed curve in the plane, maybe? Well, I just drew one. A closed curve in the plane, you have S1, that's the circle, say the unit circle, and you have the unit disk and the outside of the unit disk. Those are 2 components. It's obviously disconnected. The Jordan curve theorem is a positive statement about any closed curve. Then you worry, what is a closed curve, and so on. Closed curves dividing the plane into 2 parts. Right. So these are the kind of things that I think are very nice questions, and you end up with an interesting question. And you heard about the Jordan curve theorem, so you go to Wikipedia and you look at Jordan curve theorem, and usually in mathematics the Wikipedia articles are correct. But if it looks mysterious, you should ask me if it's correct or not. No, there are times when idiots put up stupid things, but very rarely in mathematics. You can check it, Jordan curve theory. It's this theorem about a closed curve dividing the plane into 2 parts. And then after you got to that, maybe Q5. I could go on and on and on and on. I can go on for hours. Yes, it's because I'm old. I have done this before, but you are young and you start doing it now. See, every one of these questions you can ask, right? Okay. Question 5. Do I know a manifold? A manifold in which a closed curve or even more generally, a curve is codimension 1, a hypersurface, so hypersurface means codimension 1, doesn't separate. See, funny, you have a closed curve, you have in a two-dimensional thing, a curve in the two-dimensional thing, And you think there should be the inside and the outside, but maybe there's no such thing. Yeah?
So we take the two torus and subtract the circle?
Two torus.
Yeah.
And what circle are you going? Oh, you did it.
The torus and
He answered question 5, and but actually the other questions you should answer too. But what Nico was talking about, he saw this picture, and we will even dramatize it with a color. You took out that curve, I think.
or another one around the...
Well,
doesn't really matter.
it's the same.
Yeah.
Almost. Okay, one of the generators of topology. So it's some really non-trivial curve. So somehow the manifold or whatever it is has to have some non-trivial geometry in order to do this. That's the idea. So after having this is Nico example. This is everybody's first example, but Nico mentioned it. Question 6, what is the good condition? Let's say geometric condition. So he was forced to have a geometric condition here. So what is the good geometric condition in order for the Jordan theorem to be true? I think all of you want to be and should be professional mathematicians, or in some cases physicists. I think you need to do this practice. I think it's very, very important. These technical things that you learn at university are not very important. This is important. Okay, so I'm sorry I deviated, but it just occurred to me to ask you a question. And so I asked you 6 questions and got 1 answer. Well, that's not bad. It's not bad. I think this question is the interesting question. You remove something that could be a mysterious set, but it should be close, so the complement is a reasonable set, right? And if this is connected, what happens if you pull that? Okay, so I'm sorry I got diverted here. And the main thing is here that I wanted to emphasize. Let's go back and emphasize this with some sort of color so that you know where the heck I am. This. Yeah, and this needs X is subjective. Otherwise, we don't have log. And here's the proposition, so I will prove the proposition, proof of the proposition. First, I'm going to draw a picture of the proof. Okay. So, by the way, there was a point also that I read in your homework this morning. The first remark is the image of F contains U, which is an open neighborhood of point 1. he was mixing up 1 and 0 this morning in his homework, and that's okay because I always mix up 1 and 0, so I was very happy. Okay, but 0 is mapped to 1, and the map is locally an isomorphism. This is local, it maps an open neighborhood of 0 to open neighborhood of 1. So it had, so in the image, 1 is in the image. So I'm going to draw a picture of the proof, and I think in the notes I even give the proof. I idealize, of course, the image could be just terrible, but at least it's open. Is that part clear? The image is at least open because it's locally an isomorphism, so the image is open. Right? This mapping is an open mapping because it's locally an isomorphism. It's not globally, we'll talk about it. So that's the image, and now you idealize this thing. I always idealize this in some beautiful way, but the boundary of this image could be catastrophic, so be careful, right? The boundary of the image could be catastrophic. Of course, what we're trying to show is there's no boundary, right? The image is also closed. Okay, so someplace in here is the number 1 that's in the image, and we have some catastrophic thing here on the boundary, say a point on the boundary, I don't know. Let's make it green for optimism. Greta Thunberg, green. I'm very happy about her, actually, it's great. So, there's a Greta Thunberg point is green, and now, well, now, I don't know your experience, but you should say, okay, we're going to call this point something. Let's call this point P, it's a particular point, P0, which is possibly in the boundary. There's some particular point in the boundary. And now, we know that there's an open neighborhood here, so why not take a disk? I don't know, I'll draw it as a disk. So U is an open neighborhood of the point 1. Okay? And then there is an idea here, which is the following idea. You take over here, you push it over here. You know, you take it and you go home and you smoke a cigar and drink a cognac, and you lie in bed at night and dreaming about proving a deep theorem. And the idea is, well, you can push things around, and here it is. What does it mean, push it over there? That's the key. What does it mean, push it over there? This is simply the point U times P0. You understand what I mean? I mean, I take U, so let's write it down here. This is a set of G of P0 such that G is in U. Right? I push it around. There are two different things in life. One is just pushing things around and doing things nice, and the other thing is writing the definition. Okay, this is the definition, right? Just push it around, the set of things like that. Okay? Okay? By the way, in our case, when you're thinking about this, by the way, you should say that's the same thing. It doesn't matter, probably, but just for fun, because you're a professional mathematician, you should say the group is commutative, and therefore it doesn't matter which way you write it. P0 times U or U times P0. C star is an example of an abelian group. Right? You know these words, right? What is it? Right. I thought you were going to correct my proof. Yeah, thanks. Okay. It's an abelian, you know the word abelian group, it means the group is commutative. You've heard these words, you learn a little bit about these things in algebra. Doesn't matter, I just thought I'd mention this fact, it doesn't matter here. Okay? Okay? And now the amazing thing, watch this proof. It's in the notes, but watch this proof. I take some point P1 here in the image. P1 should be here, so P1 is in here, yeah? But it's also in the image. Why can we do that? We can do that because P0 is on the boundary of this set. The definition of the boundary of the set is that. It's an accumulation point of the set. Right. There's a sequence of points that accumulates to P0 that's in this set. So I take one of them, P1. Right? So P1 equals G of P0. Right? Because it's in the set. Then P0 is G inverse of P1. Right? Isn't this amazing? I'm done with the proof. Do you get it? P1 is in the image, G is in the group, therefore G inverse of P1 is in the group, therefore G0 is in the group. At least it doesn't look satisfied. I'll say it again. So first of all, let's go through this. By definition, P1 is in this thing, and that means that P1 is G times some element. That means I can bring the G over here and to say the G inverse of P1 is P0. Right? But, well, maybe what we need is that this element, what I need is G inverse is also in U. Yeah? Well, certainly I can guarantee that because if G is small, so I will take G. I may take G very small, arbitrarily small, so the G inverse stays in here. So I will say G inverse close enough to 1, close to 1 implies G. G close to 1 implies G inverse in U. Certainly true. G inverse needs to be in U, otherwise it's stupid. Right? But if G is small enough, and I can make G arbitrarily small, because I do that by taking P1 arbitrarily close to P0. Okay? Okay. Are you satisfied? So question here, what was used here? Yeah? What was used? So let's get a little bit wild. Let G be, let conjecture. Get a little bit wild and be optimistic and make a conjecture. Remember the word, German word is Mutmaßung, or the Vermutung. The word Mut, we have courage. Yes. An open subgroup of a connected topological group is connected. Well, what did we use? We used C star. We used the topology of C star, right? We moved these things around, these open sets around, right? So we use the topology of C star. So I know I have to use the notion of topology, whatever that means. I know I have to use the notion of group. So I know I need to use the notion of topological group. And so this, to answer this question, because we're dealing with people who have no experience, namely you have to ask the baby question, PQ, what is a topological group? It's obvious that it makes very good sense to discuss a topological group. We just did it all the time. And it is a very natural concept, whatever it means. It's a natural concept, right? Topological group. It means the group actions are reasonable. It means that multiplication is continuous. It means that inverse is continuous. It means that all this stuff that you do with a group is continuous.
Do you mean connected or closed? Connected topological group is closed, I think.
An open subgroup of a connected topological group is connected.
And connected, I am more or less, it is
No.
obvious.
There's no condition. That's exactly what we prove here in C star. An open subgroup of C star is C star. Right?
What I'm saying is that a set can be connected without being in the entire set, right? So if it is closed, then it will be the entire thing.
I don't know what you're saying. You have a connected topological group, just like C star. You have an open subgroup of it, just like the image of X.
I mean, if it will be closed, then it should be the whole set is same.
You will prove, okay, I'll reformulate, you got an open subgroup is closed. That's what you want.
Yeah.
No, okay, but it's the same.
Yeah, more or less.
Maybe you actually have I see, you have a better conjecture because you're saying an open subgroup of a topological group is closed.
Yeah.
Okay, that's what we prove here. Yeah, I see what you're saying, sorry. He's already more advanced than I am, I don't know, we talk about mathematics, now you will tell me what to prove. So you're right. So what we prove here is an open subgroup is closed, right? Because it has no boundary. That's your point, thank you. Okay. Right. Okay, so that's the proof. And that's the real theorem, maybe? And those are sequences of questions that you could ask. Yes?
So when you describe P0 as the multiplication of 2 points, why does it mean it should be inside the domain?
That's right. That's right. So P1 is in this pushed over thing. So that means P1 is an element of the group times P0. Because, yeah? That's very, very good what you're saying. Yeah. So here, G in U. I said it, but that's what you're saying. Right? And I have to prove that G inverse is in U. So that what I just said to you, if you take G close enough to 1, then G inverse is also going to be in. So there's something to prove. Okay.
Why does it mean that G inverse P1 is equal to P0? It means that P0 is going to be
In the image. Because P1 is in the image and G inverse is in the image. So G inverse P1 is in the image. So P0 is in the image.
So when two two elements multiplied together that are.
Well, it's a group. It's just amazing. I'm glad, at least, I mean, he asked this, what appears in hindsight to be a stupid question, but it's not a stupid question. It is somehow going back to this amazingly powerful notion of a group. It is an amazingly powerful notion. I can't tell you how powerful this notion is. One proof that it's powerful is it was first defined in the mid-19th century. People went all over the place, not knowing really what this thing is, and finally somebody sat down and defined it. And then things exploded because the definition brought complete power with it. Let me just say, for your information, there is a wonderful German mathematician by the name of Frobenius from the Berlin School of Mathematics, many things. He really understood, I don't want to go into details, but if you like to go into details, you can talk to me privately. He really understood everything at the beginning of finite group theory, finite groups, everything, before the turn of the century, 19th into the 20th century. The definition was in the mid-19th century. So only 30, 40 years after the definition, Frobenius understands everything. It took the basic definition, basic concepts, to really start the subject. It's very interesting. Very interesting. Are we okay with all of this now? This is sort of fun, right? Okay. So, that is subjectivity. That is the fact that we have the log. That is the fact that we have this. And now we have, of course, a to the 1 over n is the key thing. And a to the 1 over n to the n is a. Right? That's one of the reasons we did this thing. And now we have roots. So this big theater just to get roots. Okay. Do I see some? No. Okay. So a bit more about the exponential map. Now we know that the exponential map is a subjective locally biomorphic homomorphism. I'm using these words loosely, but, well, you know, subjective, you know, locally biomorphic. Let's make sure you know what homomorphism means. It means homomorphism this. So phi from G1 to G2, where these things are groups, obviously, from my letter, is the homomorphisms. Means phi of G1, G2 is equal to phi of G1, phi of G2. Please get used to the fact that I do not write the operations, plus, minus, times, anything, okay? Okay, we have that. So, here's the homomorphism. And now I know a story about a great German mathematician. I can relate to that because my daughter loved mathematics and her father was a great German mathematician. Not that I am a great German mathematician, not even German, not even, But her father, who was a professor in Erlangen, which is a German town, she grew up in Erlangen. Her first name is Emmy. She grew up in a German town of Erlangen, which is a nice town, very near where my daughter studied, actually. And she grew up with a father who took her to conferences and introduced her to all sorts of mathematicians around the world. And she proved very early in her life many beautiful theorems which connected geometry and algebra. She invented certain forms of algebra. I would say Emmy Noether is the mother of a huge percentage of algebra. And Emmy Noether, of course, there was terribly sexist in those days. Fortunately, due to Hilbert, who was a professor in Göttingen, she was able to come to a small position in Göttingen. And it's very interesting, and it's very important for us, majority of us are men, there's only one woman in our audience right now, but it's very important for us to understand that sexism in mathematics is still present, but we're working on it to improve the situation. It was horrible in those days. But Hilbert didn't tolerate that nonsense and was able to bring her to Göttingen, but not in a big position, just in a reasonable position, so she could teach at Göttingen. And then Hermann Weyl was able, fortunately, Noether is Jewish. She didn't even care about any of this. She was, do you know the English word oblivious? It's a very nice English word. She was oblivious to the fact that she was Jewish. She didn't understand that this was a relevant attribute. She was more interested in groups and things of this type. And she was oblivious to it, but she was going to stay. Many of the great German mathematicians left early before the terrible times in Germany. And she did, but finally Hermann Weyl helped her get a position to a women's college in the U.S. If I recall correctly, the name of the college is Barnard. It certainly is a women's college. These colleges, by the way, are no longer women's and men's college. I went to Yale University, which was a men's college at my time, but it changed very after my time there. So most of these things are no longer women's and men's. And she went to a women's college there. Unfortunately, she had some small problem and was in a hospital and got sepsis and died at a very young age, in her 50s, I think. So she was one of the greatest women mathematicians and the mother of much algebra. When she was in Göttingen, this will shock you. When she was in Göttingen, I even saw the blackboard she's writing on. I like to look at these things. It's one of these boards you roll and you keep rolling. It's an infinite board. You roll it and it continues on. It was very interesting because in Göttingen, and furthermore at this women's college, she had all women. She had a number of women students in Göttingen. This is the importance of it. Can you imagine? I mean, Crystal can talk about this. Can you imagine having only men professors, if you're a woman, having only men professors all your life? Yes. And suddenly Emmy Noether appears, and this is a possibility of a woman professor in Göttingen, and she suddenly had women's. So she taught elementary algebra there, and she wrote on the blackboard, probably for the first time ever, the following mathematics. She says that phi be a group homomorphism. My motivation here is the exponential mapping. It is called the E function for Euler. Euler existed, I don't know how many years before Emmy Noether, and she was thinking about it being a homomorphism abstractly. Okay? Homomorphism of groups. Then she writes down on the blackboard, and maybe this is not the first time, the kernel of this homomorphism. These are the set of G and G1, so that phi of G is equal to the identity. Let me just put it here. I'll write it here one time. The identity in G2. Then she drew a picture. She drew a picture, at least in her head, and at least in the explanation, of how to think about this. Of course, this is my picture, not Emmy Noether's picture, but it's what she had in her head. And let's even call this thing N. She observes that N is a subgroup of G1. This is the first thing. So everything that goes to 1, well, here's the picture. Again, at a beginning course, you were able to do this. 1 is the distinguished point downstairs in the image group. Certainly it's in the image because it comes from 1 upstairs, right? And now let's look at everything that goes to 1. And the picture you should draw, well, 1 goes to 1. So let's hear 1 in G2, and here is 1 in G1. And here is all the stuff that goes, this is the kernel of this thing. This is all the stuff that goes to 1. So this is the picture of this thing. This is what the kernel of phi, and I wanted to call it N for short. And then you follow your nose. You follow your nose. This is this English expression. I don't know, is it in German? I don't know. Somebody German, your German.
Yes,
Is
there
it?
is immer der Nase noch.
Also, it's die gleiche Aussprache. So you follow your nose. So it's the same expression in German. In Albanian also. It's amazing. I don't know what your language is in India. What?
I don't think it's an expression.
Something like that.
Something like that. I doubt it.
That's funny. But your mother language is Russian or not? You speak Russian, of
Yeah, I
course.
speak Russian, but I have a mother language.
You have your local mother. It's a language related to Russian or no?
No, it's not.
Completely different.
Different.
Do you follow your nose? Yeah. Yeah. You follow your nose. You say you have a subset. Is it a subobject? Right? I mean, is it a subobject from the point of view of the structure? What is the structure? The structure is here group. Is it a subobject? Okay? And now you take two things in this subobject, and you check out, if you multiply these two things, then it's a homomorphism, and you get 1 times 1 is 1, and therefore it implies that the product is in there, and that's good enough. You have to check all the accents. This is just a good subgroup. Okay. Good. So this is the picture here. This is aha. This is n. This is 1 times everything you have in n. 1g1 times everything you have in n. Okay. This is here. This is the image of phi. And this is the mapping phi. And 1 is in the image, and here is everything that goes onto 1. You guys who had my analysis of one thing, you saw this diagram, always, this is the key diagram in life. Yes, you have a mapping, you have distinguished point 1 down here, you say what is the fiber over 1, right? That's interesting. And now, let's see here, we have some point over here, say G2. What is the fiber over G2? Well, say you have something here that goes to G1, goes to G2, so phi of G1 equals, let's not get, this is a terrible notation. What we need to do, and that's what you need to learn, is, that's the reason I hold lectures like this, is you need to improve the notation because it gets catastrophic, right? So we have 1 and 1 and 2 and 2 and all that stuff. I think that we're going to be trapped by notation here. I will recommend a notational change right here and now. Let's call this G and G hat. Right, and then we avoid indices, and I know it's terrible for your notes, but you can look at the video, so, right? So I think it's better to have G and G hat. Where do I get trapped? We're in pretty good shape. So we have the identity of G, and then we have G here, and now we have the identity of G hat, and now we have G hat. You see, that really improved the notation. Otherwise I get screwed up with indices. Physics people can write 10,000 indices and not get mixed up. But that's because they're smart. And mathematicians are dumb and they can't handle it. So they introduce better, yeah.
Minor remark. To check if something is a subgroup, you need to ensure that n1 times n2 inverse is in n.
You need to show that n1 times n2 inverse because you need to know that it's closed under inverse. Okay? So this is almost enough.
Because the positive, if you look at z with addition, the positive.
Yeah, but you can check. The point is that he's absolutely right. That's the first point. The second point is that I don't want to do it here because you need to do it, and you need to really. He knows because he's thought about this a little bit, but you need to think about what you need to check. The main thing you need to check is you multiply two things together, and it's still in it, right? But the inverse better be in it. That's what he's pointing out. And so it is. Yeah, you can check it. Okay. So you say n in n. This is what Abek points out that you need to prove. Actually, it's okay. Now, Eminento wrote this on the board, and if you have something in the image, you have everything in its pre-image. So let's take G1 in its pre, and now we're going to take two. G1 in its pre-image and G2 in its pre-image. Okay? And now, let's look at this thing. You have to understand, this was in advanced algebra in Göttingen in the 20th century. If phi of G1 equals phi of G2 equals G hat, right? That's the situation we have. Right? And then, let's look.
Why do you want to have it? Why do you want to have that?
Why do I want to do this?
Yeah.
I want to understand what's the pre-image of G hat.
Oh, okay.
You had my beginning lecture. The fiber over the distinguished point is, I understand it, over 1. That's by definition n. Now I take some other. I want to know the fiber over that point. Okay? And you can do it. I know you can do it. So this is phi, G1, G2 inverse equals 1. This is Abeg's point, exactly. Almost. Do you get it? Phi of G1 equals phi of G2. I bring phi of G1 on the other side. To do that, I have to take the inverse. So I have phi of G2 inverse, but that's the same thing, a phi of G2 inverse. And I put it in here, use the homomorphism property, it's that. So it says that this is in 1, is in n. That says that G1 is in, well, n times G2. And I would rather do something standard here. I would rather do this way, and it doesn't matter. And now this says that G2 is in n times G1. Right? I'd rather keep the notation like you will learn from Professor Penko, but he won't give you this picture. He knows this picture, but he won't give it. Okay. Here is the fiber over 1. Here is 1 upstairs. Maybe here is 1/2. This is the fiber 1 times n. Here is the fiber over G hat. If I take some G1 in this, this is G1 times n. Get it? Are you okay on that? So the fiber is wonderful. The fiber you get just by moving things with n. Right? The fiber you get is moving things with n. Here is G 85, and here is the fiber, whatever that goes to, is G5. I don't know. G. Here, well, let's put this, call this G. This is G hat, and this is G85 hat, and here's G85. And this whole fiber here is G85 times n. So we're trying to understand what this image is, and we understand that the image is, and now we make the big step, is the original group modulo the equivalence relation defined by multiplication on the right by n. So the image of phi equals G modulo n. The image is the group G modulo, I have a partition here. I have an equivalence relation. All of these fibers. The image is G modulo this equivalence relation. This means G modulo the right action of the kernel on G. The picture here is G, and here's G modulo n. Isn't it true? Yeah? This is trivial. But this was completely new in Göttingen in the 20th century. The people in Noether's class looked at that and looked at this, and this is a wonderful theorem. People were calling this Noether's theorem. It's Noether's remark, is this is how you should look at this. The image of a group morphism is the group modulo the action on the group of the kernel. And we have adapted the tradition in mathematics that this is somehow on the right. It could be the left. You saw me get confused. I didn't know whether it was on the left or the right. If it's an abelian group, it doesn't matter, of course. But the tradition of mathematics is the kernel is on the right. Okay? That's, in some sense, Noether's theory. I prove it. And now, I mean, all of this, you can ask your own questions here. Recall, you've probably asked the question, is the image of a homomorphism a group, a subgroup? You probably asked that question, and it should be, and it's gonna be yes. I mean, you just follow your nose, and the answer is yes. Okay? It's completely clear. If you have something in the image, 2 points in the image, and then the product is in the image. Man. Is also in the image. And inverses and all of this, you just check it. You see, if you just beat this to death with trivialities, it makes algebra boring. But algebra is not boring because it formalizes the key aspect. When you learn high school algebra or the basic college algebra, you beat to death trivialities that you hate. Yes? But if you look at what's really going on, what are the deep concepts? You see, a group, a subgroup, an image, a kernel. Yeah? And then you realize the history that it took geniuses like Emmy Noether to figure this out, what even the right definition is. You realize that it's important. Well, wait a minute. The image is a subgroup. So then you make a remark. There's a question and a remark. Remark, yeah, G modulo n is a group. That's incredible. G modulo, you take a group, you mod out by the right action of this guy n, and you get a group. It's the image. This is Noether's remark. This is her second remark, by the way. G modulo n is a group. Well, let's watch. Watch this. We'll take G modulo n. Okay, one element of G modulo n is G1n. What is G1n? That's this equivalence class. Right? So you have to have guts. I have a big one, so that's a big advantage. You have G1 modulo n, and that's an equivalence class, and you want to multiply it by G2 times n. Right? You have to be able to do that, right? You have to be able to do that, and otherwise it's somehow not going to be a group. How do you multiply? My God, how do you do this? Well, you've already done this because you define the rational numbers to be something related. You did it in my class. The rational numbers, you have these pairs of integers, right? And you multiply these pairs of integers, but there's an equivalence relation to here because 2/3 is the same as 4/6. Right? I mean, you have to screw around with that. Right? Well, it's the same thing. You have some equivalence relation here. Well, then Emmy Noether, I don't know exactly how she gave this lecture, but if she gave this lecture, she would have done it like this. Yeah, no. That's what she would have done. Well, let's watch. G1n is a set, times G2n is a set, it's pretty obvious. You don't have to be a genius. You can be just normal person like in topics of complex analysis. You want to move G2 over here so you know what to do. So you say, okay, I'll move it over, but I'll move it over times G2, then I have to correct it. So I hear that this is okay, this is good, and here I have to correct this. Then I have to study what the devil is that, and I check out that that's equal to n, and of course n is a group, so n times n is n, and that's that. So multiplication is okay. Modulo 1, absolutely fundamental thing that I put in here. The key thing is G, okay, I'll write it with the inverse on the other side, it doesn't matter. Gn, G minus 1 equals n for all G. This is the key condition that you need to make this calculation, right? I mean, you want to push everything over on the other side, right? Okay. You've seen this already, I hope, in Mickey Mouse elementary algebra, when you change bases and you conjugate. You conjugate. Conjugation is going on throughout all of mathematics. This is called conjugation. And it's true. It's true. And then so I don't know who introduced this notion, but this notion to me is called n is a normal subgroup. That's the notion. And that's more or less the same thing as G modulo n as a group. And so every homomorphism is of the form G to G modulo n, because that's the image, where n is a normal subgroup. And we have a symbol now, even in text, which is that. That triangle closed is the notation for a normal subgroup. Okay? Now that was a diversion which is not which is not in the syllabus of topics on complex analysis, but I hope it understands. So this says that X is a group morphism. It's even abelian, but since it's abelian, it makes life confusing because the conjugation just vanishes trivially. Everything cancels. So you should keep away from abelian groups because they're not realistic. So this goes to C star, which is the image of X. Which is C, which is the group, modulo the kernel of X. Which I'll just write here. In the above notation is G modulo n. And so our job is to understand the kernel of X. You see, it's the wonderful thing that if you cleanly think through things, in this case algebraically, you need to study the kernel of X. Which, let's write it down there. This is the set of Z such that X of Z equals 1. So I spent a half an hour talking about the elements of the complex numbers that are mapped to 1. Yes? It's an interesting group. So you've heard about this before this number, because when you were children, somebody said to you that you have 0, 2 pi, 4 pi, and so on, and you have, let me see here, let me go to sine. Sine, this is pi over 2, there's pi, there's 2 pi, it's periodic. Sine of x plus 2 pi n equals sine of x. And this was not even made precise really at the time of Euler. Euler really did not understand the exponential map in the sense of convergence. The only way to make the trigonometric functions precise is with the exponential map. Okay? The only way. And the key thing is the kernel of the exponential map. And we will show tomorrow, it's a trivial point once you know the question, the kernel of x is 2 pi I z. Right? Right? And that is not computer. That's the definition of pi. The kernel of x is a discrete group in the imaginary axis, which is generated by one element. So get it in your heads, please, because I've seen so many mistakes this level. Get it in your head. Here is the imaginary axis, and the kernel is a discrete group in this imaginary axis. That does not use any definitions of pi. And then you say, let pi, this is IR, and this point 2 pi I, you say, let this be the smallest generator of this discrete group, which is positive. Well, this part is positive, 2 pi. Okay. That is the definition of pi. Now, you don't have to take oral examinations. Oh, yes, you do. The examination in this course is oral. I will very likely ask you, please define pi.
Precisely define 2 pi.
Or 2 pi. No, actually, I will show you tomorrow that it's easier to define pi. Thank you very much. See you tomorrow.